Hi class. This video we're going to be discussing essentially, prime form, right? And this is going to be really the last kind of step that we're going to be taking to really understand how these pitch sets were used compositionally. One of the most important, I'm on page 512 here. One of the most important ways to classify a set is by its cardinality, C, the number of members it contains, right? For example, an interval has 2 members, a triad has 3 members, and a 7th chord has 4 members. So, 27-11 states these, right? Empty set, monad, dyad, trichord, tetrachord, pentachord, hexachord, right? Septachord, octachord, nonochord, decachord, undecachord, aggregate. Right? There we go. You gonna have to memorize this? No. No, certainly not. No. A set class is a family of PC sets related by Tn or Tni, transposition or inverted transposition. There will usually be 24 such members in a set class. The family of sets related to G, G sharp B by Tn or Tni is shown. So you can, why 24? You can take that pitch class set and transpose it to 11 other different places, right? I could transpose C to C sharp D, D, E, and so on up 11 times, creating 12 sets of the same intervallic structure starting on each of the 12 notes that we contain in the Western world, right? Likewise, we can invert all 12 of those sets. So 12 and 12 is 24. So we have a T number, look at 27-12. We have a T, or in other words, a transposed, 0, all the way up to 11, 12 of those. And then we have that transposed inversion, right? So we have an inverted transposition. So we've inverted T 0 through 11, essentially. So 12 transpositions, 12 inverted transpositions, right? Equals 24. And so for each class set class, we have 24 sets that can be used, or 24 different pitch sets at different intervals, different keys that we start on, right? Different notes that we start on that can be used to form a composition. Right? It should be mentioned that transpositionally symmetrical set, those that map onto themselves under Tn at levels other than T0, are inversionally symmetrical sets. Think about all major seconds, right? Whole steps. How do you invert? How do you invert that? You can't. It's impossible to invert. That is a transpositionally symmetrical set. Excuse me, I had to look at the book. What about an augmented triad? All major thirds. E, C, E, G sharp. Major third up is C. It encompasses an octave. It goes on forever. Transpositionally symmetrical. How do you invert a major third to a major third to a major third? It just becomes a major third, major third, major third. It inverts, right? Okay, so now you get where I'm coming at, right? And there's several other things that are out there that are transpositionally symmetrical, right? And inversionally symmetrical sets, those that map onto themselves under Tni, have fewer than 24 distinct forms, right? The whole tone scale, for example, I just said that. For example, belongs to a set class with only 2 distinct forms, where the octatonic and hexatonic scales belong to a set class that have 3 and 4 distinct forms, respectively. We talked about an octatonic scale having only 3 forms. We've already discussed this, so we've already hinted at this. We're just applying numbers to these things, right? So, the prime form is what we're really getting at here. The prime form is just taking a PC set, right? Just taking a PC set, right? Taking a PC set and essentially modding it to get to 0, right? If we can do that, right? If we can do that, excuse me, I keep finding something in my pocket here. So, excuse me. Something's poking in my pocket. If we can do that, we can move everything so the first number is 0. So let's take our normal, I shouldn't say normal, right? Just our set that we have been using, right? Which is 7, 8, and 11. We want to get to our PF, right? Or prime form. We need to make this number 0. Well, how do we get that to 0? What number would we transpose this by to get it to 0? 7 plus what equals 12? 5. T5 is the magic number. That gets us to 7 is 0. 8 is what? 1. And 11 is what? 11 plus 5 is 16. 16 minus 12 is 4. 0, 1, 4. There's our prime form, but it's not good enough. We have to check it. We have to check it against something. And that is we have to check it against its inversion, right? So what we're going to do, if we look at the book, page 514, right? It says, invert the set and repeat the previous 2 steps of the inverted set. So, 7, 8, 11 is inverted to what? It says in the book 5, 4, 1. There it is inverted. Now, normal order, get back to normal order. So we reverse it. 1, 4, 5. Okay. Now, we want to get this to 0. Well, I could just subtract numbers because I don't always have to add. I could subtract 1, that would be 0. Subtract 1, that would be 3. Subtract 1, that would be 4. Uh-oh, there's a tie, right? There's a tie. 4 half steps, 0. 4 half steps, 0. So we go to the next smallest interval, 1 versus 3. So here is our prime form, right? So we tested it against the inversion versus just our transposed, and the transposed won out. This is our prime form, 0, 1, 4. Okay? And that's what it says in the book, right? Prime form is 0, 1, 4. Normal form is G, G sharp, B. PC set is B, G sharp, G. That was what was given in the score. Normal form is G, G sharp, B. Prime form is 0, 1, 4. And the set class is 3-3. That's its forte number, 0, 1, 4. There should be 24 other sets in the back of this book. Right? We'll get to that a little bit later. Let's do another example. Let's just do a random number. Okay, let's pull a random number, a couple random set out. Let's do, I don't know, 4, 7, 9. I don't know why this number keeps cropping up. Okay, 4, 7, 9, right? 4, 7, 9. So we have to get this to 0. So why don't we just subtract 4? It's easy enough, right? 0. 7 minus 4, 3. 9 minus 4 is what? 5. 0, 3, 5. So let's see if that holds true. Let's see if that is actually our prime form. Well, what we're going to do first is we're going to, like the book says, invert it. Well, 4 plus what equals 12? 8. 7 plus what equals 12? 5. 9 plus what equals 12? 3. Normal order? 3, 5, 8. Okay. Now, let's get that to normal order. Or excuse me, prime form. Minus, let's just get it. So I could add 9 to everything, couldn't I? I could. Let's just do it. I would subtract 3, but let's add 9. So if I added 9 here, that would be what? 0. 9 plus 5 is what? 14. 14 minus 12 is 2. Or 5 minus 3 is 2. 8 minus 2 is what? 6. Or 8 plus 9 is 17. 17 minus 12 is what? Oh, what did I do here? Minus 3. Minus 3 is 5. Okay. So, here we go. We're tied again. Outside intervals are 5. But in this case, the inversion wins. 0, 2, 5. 0, 2, 5 is your prime form of this pitch class set. You were given this pitch class set in a piece of music, and you determined that indeed, not the prime form of this original pitch class set, but the inversion of this pitch class set is actually the prime form of the pitch class set. Okay? Now, if we know 0, 2, 5, we can look up its forte number, can't we? We can look up in the back of the book. Let's find our forte numbers here. I don't remember what appendix it was in. I probably should. I don't know if... Where is the answers to self-test? Ah! Appendix C, right? Trichords, right? I'm on page 559. And we said what? Our prime form was 0, 2, 5. Let's see if we can't find it. 0, 2, 5. Our forte number is 3-7. Prime form is 0, 2, 5. Great. Okay. Good to know. Next, we're going to talk about interval vectors. Buckle up for that one too. So, that is how to prime form. So up until this point, we have discussed pitch class sets. We have discussed normal order. We have discussed equivalencies. We have discussed transposition. We have discussed inversions. We have discussed transpositional inversions. And now we have finally discussed prime forms. So the last thing that we're going to discuss is interval vectors in pitch class sets. And they're pretty straightforward too. It just takes a little practice getting used to them. Okay? So stay tuned to the next video, and I will see you in a bit.